everyone, it is your companion Elle, ready to explore this massive open world of physics with you. Today, let us hack into another hidden rule of our universe. What we are unlocking today is the single biggest bug, or what seemed like a bug, in the history of physics, where classical theories completely broke down, yes, the ultimate mystery inside the atom. Bohr's quantum hypothesis and the hydrogen spectrum. Are you ready? Let us set off on today's quest.
Here are the 3 valuable skills you will gain in today's walkthrough. Treasure number 1, uncovering the historical paradox of the Rutherford atomic model. We will uncover why the rules of classical physics would cause an atom to collapse in less than a single second. Treasure number 2, the super powerful hack called the quantum condition. You will experience the thrilling moment where Bohr's discrete orbits link directly with de Broglie standing waves. Treasure number 3, the key to decoding spectra, a problem hack. You will master how to use equations from the data booklet to calculate the exact wavelengths of light emitted by atoms. Once you get these, even boss-level questions about the atom will turn into bonus stages to farm XP. Our story begins in 1885 with a strange phenomenon discovered by a Swiss high school teacher named Balmer. When you apply a voltage to hydrogen gas, it glows. But when you look at that light through a spectrometer, you do not see a continuous rainbow. You see only a few sharply separated lines. We call this a line spectrum. Balmer started by arranging the wavelengths of this spectrum in order. Looking at this pattern, he found that these wavelengths, lambda, followed a neat equation using integers n. This became the Balmer formula. R is just a proportional constant called Rydberg constant. But nobody knew why light only came out in these discrete jumps. Under the rules of the world system at that time, classical physics, it was a mystery that could not be explained. Things got even crazier. In 1909, based on his experiments, Rutherford proposed a solar system-like model, a heavy nucleus at the center with electrons orbiting around it. Do you remember this? At first glance, this model looks perfect, right? But when you apply the rules of the physics engine back then, classical electromagnetism, disaster strikes. An electron moving in a circle is undergoing acceleration. Under classical electromagnetism, an accelerating charge must emit electromagnetic waves, light, and lose energy. What happens to an electron that loses energy? Exactly. It spirals inward and crashes into the nucleus in less than a nanosecond. It is just like a satellite orbiting Earth, losing energy due to atmospheric drag and spiraling down to crash. Wait, what? Then why hasn't our body or this entire world collapsed? Facing this world-ending bug, a 28-year-old genius named Niels Bohr stepped up. Here is how wild Bohr's idea was. He said, if existing rules of classical electromagnetism cannot explain this, let us assume there is a special game specification that applies only inside microscopic atoms. He set up 2 hypotheses. These are Bohr's hypotheses, the quantum condition and the frequency condition. Let us look at the quantum condition first. Do not worry when equations pop up. Let us decode its meaning. The left side, mvr, is angular momentum, which represents the strength of rotation. On the right side, h is Planck's constant, and n is an integer like 1, 2, or 3. This means one thing. As long as an electron stays in a special orbit, a stationary state, where its angular momentum is an integer multiple of h over 2 pi, it can magically keep orbiting stably without emitting any light. This changed the rules completely. The orbit of an electron is not a smooth ramp where it can fly anywhere, like the classical physics says. It is like a staircase, where electrons can only exist on specific steps like n equals 1, 2, or 3. This is what quantized means. Quantized does not mean anything goes. It means discrete values only. Now, you might think, didn't Bohr just make up a convenient rule to suit his needs? And honestly, physicists back then felt exactly the same way. For centuries, physics had been incredibly successful at explaining the world by looking deeper and deeper into its microscopic machinery. The gas laws? They could be explained by the motion of countless tiny particles. Electric current? By the motion of charged particles. So physicists naturally believed that the structure of the atom should also be explainable by going one level deeper, using the laws of physics and mechanics to uncover what was happening inside. But Bohr seemed to be saying, no, the electron can only exist in certain special orbits. That's just the rule. What was he talking about, right? But as we will see, the conclusions derived from this hypothesis explained the observed spectral data absurdly well. Even if people were hesitant about the hypothesis itself, everyone had to admit that a fundamental truth was hidden here. Let us see what happens next. This is a grand, thrilling showcase of explaining real-world observations using a bold hypothesis. First, if you combine the mechanics of circular motion, where Coulomb force acts as the centripetal force, with this quantum condition, you can calculate the radius of the allowed electron orbits. So, let's actually calculate the orbital radius. We have two equations. The first one comes from the equation of motion, this. And the second one is Bohr's quantum condition, this one. We have multiple unknowns, r and v. Don't just start manipulating equations randomly. Lock on to your target. Let's find the orbital radius r first. Which variable should we eliminate? Yes, the velocity v. So first, let's solve the quantum condition for v. Now we substitute this expression for v into our equation of motion. Now simplify. The m in the numerator cancels with one of the m's in the denominator. R squared cancels too. And after simplifying the powers of r, we get this. And finally, solve for r. Target locked. The velocity has disappeared, and the orbital radius is now determined. The quantum condition has transformed the atom from a continuous open world into a world with specific allowed orbital radii. And because the radius depends on the quantum number n, we should write it as r sub n, the radius of the nth orbit, like this. Now, plugging in the fundamental constants, for n equals 1, the radius becomes approximately 5.29 times 10 to the power of minus 11 meters. This is the famous Bohr radius. And remember, the radius is proportional to n squared. So the second orbit is 4 times larger than the first, and the third orbit is 9 times larger. As you can see in the diagram, the allowed orbits spread out rapidly as n increases. Think of it like a geostationary satellite. To stay locked above the same spot, its 24-hour orbital period forces it into one single, non-negotiable altitude, approximately 36,000 kilometers. It can't orbit at 35,000 kilometers, and the physics engine simply locks it there. It's a similar story. But the story doesn't end with the orbital radius. If the radius of the orbit is discrete, what about the total energy of the electron? Let's find out. The total energy of the electron is the sum of its kinetic energy and its electric potential energy. The electric potential energy of the electron and proton is given by this equation. The negative sign tells us that the electron is bound to the proton, and the kinetic energy is 1/2 mv squared. Now we already know something useful from the equation of motion. The centripetal force equation tells us that mv squared divided by r equals ke squared divided by r squared. So, multiplying both sides by 1/2 r, we get the kinetic energy. This means that the kinetic energy can be rewritten as 1/2 ke squared divided by r. Now let's add the kinetic and potential energies. Combining these two terms gives us this. So the total energy depends only on the orbital radius. And we already know that the allowed orbital radius is this expression. Substituting this into our energy equation gives this. Now, when we substitute the fundamental constants, the result is this. To convert joules into electron-volts, we divide by the energy of 1 electron-volt. This gives us the result, E sub n equals minus 13.6 divided by n squared electron-volt. Because the orbital radius can only take certain discrete values, the total energy can only take certain discrete values as well. The atom has energy levels. Energy is quantized too. The lowest level, where n equals 1, is the ground state at negative 13.6 electron-volts. As you go up, you reach excited states. When n reaches infinity, E equals 0 electron-volts, and the electron is liberated from the atom. This is ionization. You made it through the calculation. Now, let's combine this result with Bohr's second hypothesis and unlock something truly remarkable. All right, here we go. Bohr's second hypothesis is the frequency condition. It tells us that the energy of a photon is exactly equal to the difference between two energy levels. HF equals E high minus E low. When an electron warps, or transitions, from a higher step to a lower step, it releases a single photon carrying the exact energy difference. Depending on this energy difference, the color of the light is set by E equals HF. Conversely, if light with the exact energy difference hits the atom from the outside, the electron absorbs it and jumps to a higher step. This was the true identity behind the line spectrum that Balmer observed. How does that sound? Pretty amazing, right? But are you still wondering, just like the physicists back then, why is angular momentum quantized in the first place? 10 years after Bohr proposed this, in 1923, a physicist named de Broglie unlocked the true meaning of this secret command. De Broglie said that electrons are particles, but at the same time, they are also matter waves. The wavelength is lambda equals h over mv. He arrived at this hypothesis by thinking, if light, which was thought to be a wave, behaves like a particle, shouldn't an electron, which was thought to be a particle, also have wave properties? If an electron is a wave, to exist stably, shouldn't it form a standing wave? Standing waves are stable, right? In other words, when the wave completes one full orbit and comes back around, if its crests match crests and troughs match troughs, it stays stable. Otherwise, it would interfere with itself and cancel out. Yes, only when the circumference of the circular orbit, 2 pi r, is an exact integer multiple of the wavelength, n lambda, can a stable standing wave be formed without destructive interference. 2 pi r equals n lambda. Now, substitute de Broglie's wavelength, h over p, which is h over mv, into lambda in this equation. And this equation right here is the bridge between the wave nature of matter and its particle nature, captured by momentum. Rearrange this equation and you get mvr equals n times h over 2 pi. Bohr's quantum condition was literally the condition for an electron to form a standing wave. Isn't that mind-blowing? Time for a mini quiz quest! Let us get your brain engines running. Here is the question. For an electron in the n equals 4 orbit, the third excited state, of a hydrogen atom, how many complete standing wave patterns, made of crests and troughs, are formed along its circular orbit? You have 3 seconds. 3, 2, 1. Time is up! The answer is 4. Just as shown in the equation 2 pi r equals n lambda, the principal quantum number n directly represents the number of wavelengths fitting along the orbit. So for n equals 4, it forms a standing wave where crests and troughs repeat exactly 4 times in one full loop. Could you picture it instantly? Awesome! Your understanding of the mechanics is solid now. But simply understanding does not farm game XP. Let us roll up our sleeves, do some hands-on work, and train our players' skills to defeat actual final exam-like monsters. Here is our short answer style quest. An electron in a hydrogen atom transitions from the n equals 3 energy level to the n equals 2 energy level. Calculate the wavelength lambda of the emitted photon. Let us solve this puzzle together. The steps are simple. Step 1. First, calculate the energy difference, delta E. Using our formula, delta E equals E3 minus E2, which equals negative 1.51 electron-volts minus negative 3.40 electron volts, giving 1.89 electron volts. Great! Now we just need to find the wavelength of light corresponding to this energy. Here is a super important warning. Do not plug values directly into the formula in electron volts. The unit for E in E equals HF must be in joules. Let us convert it into the standard physics unit, joules. 1 electron volt equals 1.60 times 10 to the power of negative 19 joules. So, delta E equals 1.89 times 1.60 times 10 to the power of negative 19 joules, which is approximately 3.024 times 10 to the power of negative 19 joules. Now we are safe. Step 2. Next, use the photon energy formula E equals HF, which equals hc over lambda, and solve for the wavelength lambda. Another bridge appears, but this time it connects the wave nature of light to energy. Call up Planck's constant, h equals 6.63 times 10 to the power of negative 34 joule seconds, and the speed of light, c equals 3.00 times 10 to the power of 8 meters per second, from your data booklet and plug them in. Lambda equals 6.63 times 10 to the power of negative 34 times 3.00 times 10 to the power of 8, all divided by 3.024 times 10 to the power of negative 19. This gives approximately 6.58 times 10 to the power of negative 7 meters, or 658 nanometers. There it is, 658 nanometers. This corresponds to red visible light. This is the exact wavelength known as the H-alpha line in the Balmer series. Quest cleared! What a clean defeat! That was fantastic execution. Now, let's zoom out and see where this newly unlocked quantum ability takes us in the wider open world of physics. One of its most powerful applications is astrophysics. Thanks to these discrete energy levels, we can determine the chemical composition and even the temperature of stars thousands of light years away, simply by analyzing their light spectra. How was it, team? What seemed like a completely meaningless, discrete line spectrum was beautifully unlocked through a collaboration of classical mechanics, quantization, and standing waves. Bohr's bold hypothesis of the quantum condition, the quantized energy levels derived from it, and the mystery of spectral lines solved by them. When we discover this beautiful line of code hidden in nature, the resolution of our world steps up to a whole new level. Calculation problems might look like tough bosses at first, but once you understand the system mechanics and farm enough XP, you can definitely beat them. You can absolutely master this. Believe in your potential and keep pushing forward.
If you enjoyed today's walkthrough and earned some sweet XP, hit that subscribe button and like the video to join our Adventurer Guild. Drop a comment below if you have any questions or if there is a specific problem you want me to hack next. See you in the next quest. See ya and keep exploring.